Hello everyone, True Zero Emissions here. Okay, so before I wrap up for the evening, well, I never know when the evening's going to end, because if I have some ideas in the middle of the night, there will be no hesitation to be drawing out the ideas, taking notes, and even doing experiments. But meanwhile, what I'd like to share with you is some different ideas about this idea of the Bloch wall, B-L-O-C-H. I think I'm spelling that correctly. You could research and study the Bloch wall. Bloch wall is named after a famous scientist, if I understand correctly, a famous researcher, inventor, a theorist, a theoretical experimentalist, an experimental theorist, a gentleman that discovered that area in a magnet, right? If this is a magnet, and if this is north and this is south, somewhere between those two areas, there's no field there, there's no reading, right? So if my meter that reads north and south will not read anything there. If you look at the previous videos I just uploaded, and there's one uploading right now that's going to probably take a few hours or possibly a few days because it's a long video. It'll probably be up within the next few hours. I'm talking about that and showing some, I think in that video I show some experimentation where I'm using the meter to read that space and how I can move that space by attaching more magnets to the end here. It moves that wall, it moves that zero area, right? Which makes sense, right? It makes sense because when you add magnets to a magnet, the magnet acts as one magnet, so it makes sense that that space would move. But if we take a magnet, instead of attaching it to the magnet to make it longer, if we just pass it by here, if we just pass that magnetic field by this, right, then it can shift that Bloch wall for a moment, and then the Bloch wall will go back when the field leaves, when it leaves this area of that rotating magnet that's moving around, right? And that shift allows our copper wires to, I don't know if we'd call it induce a current in a voltage, or if we just call it, the image I see is basically, from what I've read, is that electrons come from the Dirac C-holes. Does that mean that electron pairs go from, like Don Smith talked about the sun. I don't know if it was Don Smith or a student from MIT, but speaking at one of Don Smith's lectures and demonstrations, but it was talked about by people that know a lot about science and about the universe, that the sun produces electron pairs. One large electron and a small electron will team up together, they come together, and when you send a small amount of I don't know if we call it potential or voltage or current. I'll also call it voltage for the moment because Don Smith was working with high voltage and basically almost no current, if any at all. And that voltage can push those electron pairs apart. And when they come apart, they release an energy pulse like a voltage. And then when they come back together, they release current. And that voltage and current can be captured by coils. Now, what I just said, I don't know if that relates to this particular experiment, but I'm just sharing with you where my imagination is going, right? And Einstein said imagination is more important than knowledge, and we must never forget that. And it doesn't mean don't go to school, it doesn't mean don't study. It just means that if anyone ever tells anyone that we cannot do something, that person is only talking about themselves and anyone that may have told them that, right? It doesn't mean that's the way the world works, because we actually live in an infinite inevitability universe, and that comes from the greatest minds on this planet. So not only are all things possible, all things are inevitable. That's just the way it is. That's science for you right there. So let's talk about this. If we have, I'm going to talk about a couple different ideas. So this is a magnet here, this is a magnet here. I think these would be a lot closer together. I'm guessing they would probably be like this magnet would probably be within maybe an inch. When I researched Don Smith's rotating separator coil, it looks like he has the two sets of magnets very close together. And then they're in tubes. He has them in PVC tubes with a cap on each side, and then those are slid into wood. And excuse me. And the wood has a cutout where the pipe can fit in there. That's what it looks like. And then copper wire wound around the pipe, right? Because magnetic flux can travel through plastic, so that wouldn't be a limitation. And I guess the distance is also not a limitation, right? I would think it'd be more efficient if the wire was directly on the magnet, but even if it's like a quarter-inch away or further, maybe it's still okay. Only testing will tell us that, right? It'll tell us the difference in efficiency. So of having the copper wire directly on the magnets versus between, like if the magnets are placed inside of PVC pipe, and then if there's a space, like a quarter of an inch of space between the magnet and the actual copper coil wire that's going around the PVC pipe, right? If we were to put those in pipes. Now, another idea I'm thinking of is, instead of using two magnets, now, first of all, in Don Smith's system, he's using very special materials that interrupt that field in here. So when these two magnets are attracted, okay, let me think about this right now. Let me think about this. I just want to visualize the Bloch wall, because right now, the Bloch wall is going to be in the middle, right? Well, if the magnets were separate, it's in the middle. Okay, so if we put something in here that blocks this field, then the Bloch wall, the zero, between north and south, right? So this is north, south, north, south. So we have a south and a north here, so they want to attract. Now, if we block that field or move the magnets away from each other, that zero field area is right here. The Bloch wall is right there. But if these magnets are close enough together, that let me think about this. Moving these magnets together, I think this would move. I think it would move over here, right? I don't know how far. Actually, if these magnets were touching each other, I don't even think this would be here. This is just my own thoughts. I think this would move to this area where the magnets were touching. And then when the magnets come apart, this would move over here to the middle again, as long as there was no effect on one another here, the magnetic effect of these two magnets pulling on each other. Any effect between these two magnets that can be felt or even not felt would still affect that Bloch wall, right? It'd move it over that zero area between the north and the south, right? Between the north and the south areas, right? So, so what Don was doing, I think what he was doing is he had these close enough that the Bloch wall must have been close to the edge here, right? These were close enough together. And then when he interrupted that field by sending something between here, a special material, he also talked about using neodymium dust, magnetic dust, right? And then spraying adhesive on a record player and spraying the dust, that magnetic dust, onto the record player, and then having cutouts in the record player that were at least as large as these magnets. And when that opening passed through here and let the Bloch wall move, and then when it was solid neodymium dust again, then the Bloch wall would move back. So there's that shift, right? Boom, boom, shifting like this, like pulsing, pumping that energy in from the 0-point field into the copper coils, right? Okay, so now I'm going to talk about another way I'm thinking about testing this is one magnet here, and then over here, instead of having a magnet, having just a ferrous metal, ferrous iron, which is it's not polarized, it's just iron, but a magnet can stick to it, right? But it's not magnetized yet. So putting that here, moving this magnet close to there, and then interrupting the field between the two, the same way we interrupted the field between the two magnets. Same thing. We have a, you know, something come between there and cutouts, and then the neodymium magnet dust glued onto a record, for example, and then coming between there. Now, the simpler way to do this is supposed to be, just my research and study indicate, I could be wrong about this, but it's supposed to be just using a magnet here instead of using a thin record, like a record from a record player, and then cutting it out and then putting the adhesive and the neodymium dust, and there's other materials as well, bismuth, I think, and there's another one. I don't know if, I can't think of the other word. I don't know if it starts with a T or what it is. Don Smith talks about it a lot in his videos. If you study all his videos on his lectures, he talks about the materials he used for the Bloch wall, to shift the Bloch wall. And I'm not sure he uses those words, but that's the words I'm using because that's how I understand it right now. But to use a magnet, and I could see how a magnet would do this. Now, a magnet, so he was using milliwatts to spin the record, right? I think with a magnet, it would take more. It might take actual, you know, a lot more energy to move the magnet past here, because the magnet's going to want to stick to this, and it's going to want to stick to this, whether this is a magnet or just ferrous metal, right? Which is just metal that a magnet will stick to. It's going to want to slow down and stop right here. But we want to keep that going, right? We want to keep it moving. So the nice thing about this, though, is because we're using the Bloch wall shifting. So here, when the cutouts open, when it's cut, the cutouts open, when we come between the space here, and this connects, this is going to become polarized. This metal is. So if this is not a magnet, this is a ferrous metal, right? And when this field affects this one, I think there's going to be, I don't know if there'd be a north and a south. I'm not sure. I have to check. But I know this would become magnetic. And then we have copper wire going around this, right? And then when this magnet goes out of the area, away from it, what does this do, right? Or do we just take this magnet out and then rotate a magnet past this ferrous metal, right? So now we have a magnet passing this, and there could be a magnet, a space, a magnet, a space. And so we have these magnets pulsing this, polarizing this intermittently. And then the coil around this iron, this non-polarized iron that's intermittently switching between polarized and non-polarized, is inducing a voltage and a current. And if I'm not saying that correctly, forgive me. Use your own words, do your own research. But I'm just trying to share imagination right now, right? So the words are not going to be perfect. But I'm trying to paint a picture of an experiment that I can use magnets to charge my batteries. So the question is, how can I charge my batteries with magnets and copper wire and motion in the most efficient manner possible? The question is not, can I do this? Yes, I can do this. The question is, how can I do this most efficiently? If we go on the internet and we say, I have an idea, can I do this? If you're talking about the future and something that's never been thought of before, do you think people are going to say, yes, you can do that, you should keep trying to do that? I don't see that. I see a lot of discouragement for things that we have not yet imagined, or that have been imagined and been tested but not yet achieved in great degrees of efficiency. We have to not give up. We have to keep experimenting. Never, never, never give up. Remember? Never forget that. See you in the next video.